So we've got 4 papers. I see we've got a decent audience arriving, so welcome to everybody. I'm Richard Green, I'm chairing this session, and I'm just giving it a moment or two for people to arrive. I see that we've now got 3 of the 4 speakers. I think we've got yes, we've got 3 of the 4 speakers at the moment, and so I think Lisa, welcome. So the way we'll be running these sessions is 20 minutes of presenter speaking and then 5 minutes for discussion. Given the difficulties online, I think even if you've got an urgent question, could you put it into the chat, and I will keep an eye on the chat. And then if you could put your virtual hand up, which on the new version of Zoom is the one that you have to do a reactions at the bottom of your screen and then raise hand, and that will come up in the presenter bar that I will be able to see. And therefore, if you have any, when we get to the discussion, we will do it that way. So we have got 4 papers on, most on 3 of them on electricity market integration, and also a modelling paper also looking at the future of electricity markets. And if I could ask Lisa Ryan to start presenting her work with Eva Lazarczyk on the integration in Europe, please, integrating European electricity markets. So 20 minutes, Lisa.
Good morning. Oh, excuse me. Good morning, and thank you for chairing this for us, Richard. Is it okay if I share my screen then?
Please do, please do.
Yeah. So I'm just and I just need to put that on. Is that visible for you all?
Yep, that's good.
Okay, great. So I'm delighted to be here, even though it's a bank holiday Monday in Ireland. I didn't quite foresee that with the dates, so an early start. But today I'm going to speak to you about the Irish case study of integrating electricity markets. This is co-authored with Eva Lazarczyk, who is from the University of Reykjavik, in the business school there. And I am in University College Dublin from UCD Energy Institute and from the School of Economics. So the format is going to be pretty standard, and just introduce you a little bit of the background thinking to this paper, and what are the main issues that we're going to focus on. The reason we're working on this is because Ireland provides kind of a natural case study, as we did integrate our market into the European electricity market in 2018. And then we will carry out some estimation with some conclusions. I should say it is quite preliminary work, so I suppose the analysis is quite a simple analysis so far. I'm really hoping to get some feedback from you today, and some ideas on what we should do with this work, because this is my summer project and I'm looking forward to continuing further work in this area. So I think probably most of us in this session are familiar with electricity markets and the rationale behind the change to design of electricity markets, and particularly in the case of countries or markets with high shares of renewables. And by renewables, I am mainly talking about variable renewables, asynchronous renewables, like we have in Ireland, which is mainly wind. And I think there is a growing literature out there on how markets are no longer fit for purpose. So I guess there's 2 things: the variable renewables in the market, but also liberalization of markets mean that we don't have the vertically integrated utility anymore. And so this situation with the merit order effect means that prices have been falling in wholesale markets. Companies, they bid their short run price when they're bidding, and so this has led to a situation where companies are not recovering their costs, and the long run costs in particular, and the missing money problem. And so this is just a general issue, and this is sort of the rationale for revising the design of markets. Other issues, I suppose, in general on this, when you have high shares of variable renewables, is that we have a requirement for ancillary services, for flexibility, to be able to facilitate those high shares, and we need markets to be able to incentivize those services as well. As I mentioned, we have liberalization of electricity markets. And so overall, the idea is that we will integrate markets to achieve a few points. One is to enhance their economic efficiency, to reduce market concentration if you have more players, to strengthen the security of supply, and reduce reserve capacity. I suppose these four features are extremely relevant for a small isolated system like we have in Ireland, where we have historically had high market concentration. We really do risk a security of supply because we are very poorly connected with other markets and other systems. So we do have a risk of basically the lights going out. So the idea of market integration at a European level was, I think, more about enhancing economic efficiency particularly, but in Ireland it also is very important for these other reasons as well. I suppose just as background, we always have to keep in mind, although a lot of the time people working in electricity are very focused on the security of supply issue, but the other two aspects, competitiveness, and by competitiveness I mean for companies, both for the suppliers, the generators, all the players in the market, but also for affordability for householders. This is a competing challenge. And sustainability, of course, now increasingly we have to decarbonize the electricity system. And so sustainability, this challenge to decarbonize our system while retaining a very strong security of supply is extremely important. And I should say, well, I'll come back to some of this again. This is just a sample of some of the literature on market integration. As I was starting this project a couple of years ago, while starting to think about it, I started reading to see what other work has been going on. And we have very old work talking about spot pricing and the rationale for spot prices, and in some ways it is the grandfather of a lot of the work that has carried on since then. There have been some empirical, there's quite a lot of theoretical analysis on market integration. There has been a little bit less, I think, on the empirical sort of real case studies, which is why I was interested in looking at the Irish one. We see Pellini did it on the Italian electricity market. It's a little bit older now, from 2012. There have been a few papers, from the CEP or from Newbury in various groups. One is estimating a piece of work that was carried out for the European Commission. I think back in about 2013, there was a series of reports carried out on estimating the benefits of integrating European electricity markets that was then published as a paper. And there it's quite interesting to see how there are significant benefits to electricity, and they estimate there's about 4 billion in benefits by integrating European electricity markets when it's extended out to the 28 member states. Another paper by Newbury is just talking more generally about the features that we need to see in an electricity market when we have very high penetration of renewables in an electricity system. And many of these points are extremely relevant for us in Ireland. And an interesting paper from Dauphine is on the US, looking at integrating some of the markets on the Western United States and the benefits well, I suppose the impacts on prices and emissions in those states and in those markets. And it shows that it's not always straightforward, that there aren't always straight benefits. Then there are last two papers here talking about European, so the Pollitt paper is talking about Europe's electricity market design, so looking out to the future, what needs to happen. And the last one it was relevant for this work because they are looking at how we can measure inefficiency in electricity trading. So it's not just enough to be promoting more trading, but we want the trading to be going in the right direction so that we have an efficient electricity trading. So this is just a sample, but there is quite a lot of theory out there. But I think from this sample, but there are probably other papers. I'd be delighted if any of you would like to flag any to me on, you know, electricity markets, as you know, are very specific and locational specific. So there are, while we can draw some general conclusions over what is a good idea for market design, when you start to get into the empirics of analyzing particular systems, obviously every system is quite different and it's difficult to compare. And with the result, I think that there hasn't been that much published on analyzing, you know, real case studies. So if I come to the European situation, this is from 2016, so maybe more interconnection now. It's just to remind those of the international audience, Ireland is that little blue country on the edge over there. You can see the interconnection across the European continent. Some are already coupled, some were planned at the stage in 2016. At that stage, Ireland was being thought of as the ISAM. So in Ireland, we had the SAM and was being considered to be, it was already interconnected with the UK market, with GB. I should say that the Irish market is an all-island system, even though we have two jurisdictions, Northern Ireland and Southern Ireland. But it was connected with the UK system, but was not part of the overall European target model at that stage. And so we are focusing on Ireland here as an example to see, I suppose, to examine the impacts of the integration of an electricity market. And I suppose just the context for that policy change, it was partly it was 100% in compliance with the EU internal energy market requirements. Ireland received a derogation from one aspect of the legislation, so we were allowed to integrate later. And it's partly to do with the nature of the isolated system. Irish regulators were able to argue successfully that, you know, really a lot had to be done to make sure that this could be done successfully without any supply issues. So, you know, it was derogated a few times until October 2018. I think probably the third energy package was the directive that came in 2009. It brought in many very important sort of far-reaching changes for the European electricity, and not just electricity, but gas as well. It brought in a liberalised internal market. So many of these changes were already put in place in Ireland. We were one of the first countries to liberalise the electricity market and to break up the incumbent. It introduced this idea of a target model, which would integrate and provide the design for electricity markets across Europe. And it created an internal energy market. The idea being to have efficient wholesale prices across Europe and to improve efficiencies. So in capacity market is measured there. That's not going to be considered in this paper. We've looked at another piece of work on the capacity changes that came to the market in Ireland, but it was something that was deliberated across Europe. Some countries have capacity markets. We had a capacity payment in the past, and now have moved to an auction-based capacity market in line also with those regulations. And overall, of course, the objective was to deliver a secure electricity system and to decarbonize it. We also have a target of a renewable obligation of 40% under the 2020 climate framework, to have 40% electricity in the system by 2020. So, okay, so this is the Irish power system, just in terms of the fuel mix. This data is from 2018, so the latest data that came out is in 2020, which refers back to 2018 data. You can see that we have an awful lot of gas in the electricity system, and there is some coal and peat, and particularly the renewables part is growing. So I suppose that I wanted to show you next slide. We had a 40% target for 2020 in 40% for renewables, and my next slide is stuck. This is the contribution of renewables to the gross electricity consumption, and you can see that the red is wind. It's really mainly wind. We have a little bit of hydro that's been stable, that's been there forever. It's never going to change. So all of our I suppose efforts in terms of increasing renewable electricity and the share of renewables in the electricity system is coming from wind. And this, you know, obviously poses a very big challenge to the system in terms of physics, but also in terms of making sure that the electricity market works, because we still have a lot of gas, and gas definitely provides the capacity for when we don't have any wind. But their wind is very important, and it's forecast to grow. The plan is to get to 70% renewables by 2030, and again, it will be all wind, onshore and offshore wind. So the big growth is going to be offshore wind in Ireland in the future. Okay, so if we look at the changes that came to the market, so we had before the market was integrated, we had the Irish single electricity market, and that was very novel in its time because it transformed. We had two jurisdictions, as I said, Northern Ireland and the Republic of Ireland, and it was an all-island market. So we had one wholesale electricity market from two jurisdictions. There were really three components: the energy market, capacity, and then constrained payments. And so the focus here is on the energy market part of it. It was a centralized wholesale pool, generators and suppliers traded. And the final price was settled 4 days after the trading day. Capacity payments were paid to all based on availability. But the interconnectors, so we have two interconnectors, they were reserved to flow power in line bilateral trades. So they didn't run very efficiently. If we consider efficiently to be flowing in the direction from high price to low price, sorry, low price to high price, you know, because you had to bid, similar to many parts of Europe, you reserved capacity on the interconnector, usually a day ahead of time, and so the prices may have changed in the meantime. So it wasn't always very efficient, and it was actually quite difficult to get data on interconnectors previously because they were bilateral trades. So from the 1st of October 2018, the new electricity market came into play. And this is something that, was really planned, talked about, for, let's say, 4 years in Ireland beforehand. It required enormous effort to change the way the market was run. So there were new markets added in line with European markets. We now have a forward market. There's the day-ahead market, which is most similar to the previous wholesale market. Now we have intraday, and we have a balancing market. And obviously the idea is that this will be facilitating increased trading. The vast majority of trades happens on the day-ahead market still, but we had very little liquidity previously. So the forward market, the idea is that it will start to see some trading and liquidity in that side, but so far it has really been the day-ahead market where the majority of trades are happening. Okay, so the data that we have is from the year and a half before the market change and the year and a half of post-market change. So we have Irish price data, wind generation, imports, and then system demand on the market. And what we're doing here is quite simple econometric analysis, looking at the impact of the change in market on the wholesale price, the day-ahead price, and also on imports. Just first of all, the flow in terms of the level of trading that's happening, and then we look at the efficiency of those flows. And the idea is that we will take this further now that we have, as the longer we wait, the longer our time series is growing since 2018, and we would like to continue with this data set for a while longer and develop it more. Yeah, okay, that's just in terms of show you. So that black line in the middle is October 2018. So this is just wholesale day ahead prices. And you can see that, I probably should have put a slide here showing what we're expecting, what we would like to find if we were in line with economic theory is that electricity prices should fall, to drop a little bit after integration, and also that interconnection, that the trades on the interconnectors should increase. I should have said that from the outset in terms of what we are looking to see, whether it's in line with expected theory. Now, if you look at, this is just day ahead prices, hourly day ahead prices, and you can see that overall, post October 2018, the prices don't look like they have fallen just by eyeballing this graph. They do look maybe a bit more volatile, perhaps, This could be to do with just the new market coming into play. There was considerable, I think, anxiety might be the word, from a lot of the players in the market as to what would happen here. But you can see that overall it does not look at first glance that electricity prices have dropped in any way or dramatically. Although actually, as you can see, as further on and as you go further to the right, they do look like they were settling a little bit. So this is definitely to be tracked further. And on the interconnector flow, you can see that it has been, much more used. So now it's reaching capacity since the advent of the ISEM, since October, and since then we have, in both directions, it is being utilized to its full 500 megawatts is the capacity of that. So EWIC is the east-west interconnector between Ireland and Great Britain. So the idea is now to look at a little bit more details, just to see if you were to model the wholesale prices. So we have as our dependent variable price, the day-ahead price, and our independent variables are the wind generation. Firstly, in the first instance, wind, system, demand, and just a dummy for peak time. And then we have, in the second and third, we have included a dummy for the ISEM, so since the ISEM market, and then we have an interaction term to see whether the ISEM and peak together make a difference. And these are hourly data. We do the same for import in terms of just the total trade at any period of time. And it's, we're modeling against the wind and demand and wholesale price, and then peak. And we again have a dummy for ISEM, and we have an interaction term between ISEM and the peak. Okay, so if we just look at our first results in the simplest of the models, when we're looking at wholesale prices against wind, system, demand, and peak period, you can see that, well, everything's significant actually with the number of data points that we have. So we can take that for granted really, but that the signs are in the right direction in that as wind increases, prices are falling, or have fallen. Higher system demand creates higher wholesale prices, and during peak periods, wholesale prices are higher as well. When we put in a dummy variable for the ISEM, this is where you see that it's a little bit not what we expected. Since the advent of the ISEM in this data period, wholesale prices have risen. But when we include an interaction term, part of that is at the peak. So since the ISEM is in place, at peak times prices are higher, but a lot less than overall prices. So the prices during peak periods are a smaller share than what you see overall in terms of the ISEM impact on prices overall. So that is the first one. So in summary, just in terms of the prices, we see that wholesale prices increase when system demand increases during peak periods, and since the introduction of the ISEM, and also during peak periods of the ISEM, and wholesale prices decrease when wind production increases. So that is to be expected. If we look at the imports model, here we see that, so we model it first with the Irish price. So we do it twice. We have GB prices and we have Irish prices. And when Irish price increases, then you have imports. When at peak periods, you have more imports. When wind is generating more, you have exports. When you have a higher system demand, you have significantly greater imports. When you put in a dummy variable now for the ISEM, we see that the advent of the ISEM has increased imports, but during peak periods, and since the ISEM, there are more exports during peak periods, probably because they are also peak periods for the UK. They'll be very aligned in terms of peak times. And if we look at UK prices instead of Irish prices, we see that higher UK prices have also caused imports, and otherwise the trends are roughly the same. So the trends are the same whether it's UK price or Irish price. And then here, instead of taking either the Irish or the UK, it seems probably better to take a ratio of the two to see what that differential is. Here we divided them, and you can see that when the Irish over the UK price increases, you do get a small increase in imports as well, which is what you would like to see. And peak periods are, but during peak periods there's higher imports. Wind generation causes exports, and system demand causes increased imports as well. So here's just the same again, except for now we've included a dummy variable for the ISM. So since the ISM has come in, we have also an increase in imports. So that doesn't really change the dynamic, whether you use which of the prices between Ireland, UK, or the ratio between them. It doesn't really change the signs on any of these variables. And similarly again, actually, when you have interact the peak at the ISM, then you see that there is a decrease. Okay, so how am I doing for time, Richard? I'm very sorry, I didn't look at the beginning to see where I was.
You're actually slightly over. I gave you a 5 minute earlier. I don't see any sign of our second speaker running out, which is why I have been slightly less nervous. And I sent him a direct email as well. Our session host doesn't know anything, so you have got a couple more minutes, but
okay,
not too much more than that, because we want to have a bit of time for discussion, please.
Okay, no problem. Okay, then I'll quickly just show you these. The Montoya paper that I mentioned at the beginning talks about the efficiency of trade, and this is obviously a point of discussion for others as well. So we decided to look at that briefly so far. And just looking at this graph here shows, I'm not sure if it's quadrants basically, where you have on the x-axis the Irish GB price differential, and on the y-axis you have imports and exports. And you can see that basically, well, you can't see much. It's a bit of a mess, really. All the points are clustered around. You can't see any trends really, except for that it's all kind of clustered around the center. And this is before we had the ISM. And since the ISM has come into place, you can see that things are a lot neater, and they're clustered along the interconnector capacities. So we have two interconnectors, and together they make up 1,000 megawatts. But you can see that when the price differential is positive, then you find imports, and when the price differential is negative, you're more likely to find exports on this side. So that is what you would like to see. And so we did model that in terms, so what I did was here, it's just the N plus is the count. There are different ways of doing this, and so I followed some of the recommendations in the Montoya paper. We've counted if the trade is going the right direction, what is being compared with the price, you count it. And so I've counted those together and just regressed them again against wind, demand, the dummy variable for ISM. And you can see here that when the wind is blowing, you find that the count of trades is going the right direction. For demand, it's a little bit not so clear, it's negative, but for the ISM overall, you can see that it's, there's quite a strong coefficient there. So since the ISM has come into play, we have definitely interconnector flows seem to be operating more efficiently, and also at peak times. Okay, I'm going to just skip through that and go to my conclusions. So overall, yeah, we don't see indications that wholesale prices are falling. Now, I am interested to go back and get more data now for the last year and see whether this has changed now that the market has really settled. But imports do appear, the trades overall, they seem to have increased. And we have, I think, with a longer data set over time, we will have definitely a more robust estimation. Our idea with this, as you've seen, it's just a simple OLS regression. And there's a lot going on in these markets. So what we would like to do is to use synthetic control analysis. We've chosen Spain and Portugal because they are other European member states, obviously, but also because they're the only two we can find that has the same kind of level of wind in their system. I mean, Denmark does as well, but they are so interconnected with Scandinavia, and also the fact that they have access to hydropower there, that it just seems that they are less isolated. So Spain and Portugal were the ones that we were going to try first, to use those as counterfactuals, and then to examine some of these variables again in terms of the interconnector flows, but also I think just the volatility of prices and how the peak variable looks, and peak prices, what do they look like? They are the next steps, but I would really welcome any feedback or ideas that you might have. And that is it for now. Thank you very much.
Okay, thank you very much, Lisa. So I say I'm still not seeing any sign that Fabien Roques is here. He should be presenting now. But do we have any questions? Can you please, if you do, you could put, the easiest thing is to raise your virtual hand. So that should be on the reactions bar at the bottom of your screen. If you press on that, as well as all the claps and thumbs ups and other fun things we've been getting used to, there should be the chance at the lowest option to raise hand, and that would then become visible to me and to others in the participants bar. So not seeing those. Lisa, did you have any? So Nicolas, your hand is up.
Yeah, thanks. I mean, it's a very straightforward question. I guess we didn't have time to get into this in 20 minutes, but how should we think about all the possible confounders that occurs in these kind of studies? Because you don't talk about natural gas prices, you don't talk about what happened in the UK, or maybe like the market reform also like transfers some revenue from day ahead to intraday or dispatch markets. So I mean, did you have time to do kind of robustness checks along these classical confounders you see in these kind of studies?
Yeah, we have considered them, and I wondered, I mean, our challenge is to try and consider them quantitatively. In the paper, as we will write it up, we will consider them certainly qualitatively and discuss what's going on in the different markets. Like the gas prices that we have there are monthly gas prices, and just because we know as well that the generators, they also have their gas prices are usually hedged. It's true that we did have them in at one point, and I took them back out again because it just seemed that there was such a lag between the gas price and the wholesale spot price. But yeah, it is a big factor, obviously, in determining the wholesale price. In fact, it's the only factor. So it is one that we should probably think about again. I just wasn't confident of our data at the time as well. In terms of the other confounding factors, yeah, it's true that, I mean, that's the limitation of econometric analysis, I think, that, it is quite limited. So I'm not sure. I mean, do you have any ideas in terms of, how to consider them in, aside from just discussing it separately?
Yeah, I mean, I guess we can talk about that. I mean, I don't do much work in this area. Usually like some instrument, I did some attempt to instrument which are more or less credible depending on the setting, but I guess the discussion of it would be helpful, especially since so many things are changing at the same time on the
that's right.
SAM, and you're only focusing on day ahead, so so many things could be happening.
Okay. Thank you.
Again, thank you, Nicolas. I'm keeping an eye for hands. Otherwise, one question, anecdotally, I believe some of those links across the Irish Sea have been out of action some of the time, and particularly the data you showed quite early on with an awful lot of 250 megawatt flows. That sounds like one cable out of two is working, and perhaps the interconnector was at capacity. Have you thought of trying to adjust for those limits?
Well, it's one thing, we need to go back and put in, I think, some of the outage data and the interconnector to check it again. My understanding, you're right, there were periods in 2018 where the interconnector was out. And yeah, well, I haven't included that in the data right now, but that's a very good point. I need to make sure that that's correctly incorporated. Thank you.
Okay, well, thank you very much. I say I'm being a bit flexible on the timings because it looks as if our second speaker is a no-show. And I say I have sent a direct email. The session host has sent a direct email, and there's no sign that he's in the session himself. So in which case, could I now invite Clas Eriksson to start a little bit early. So with apologies to anybody who's going to turn up halfway through Clas's presentation, but I think that's probably the efficient thing to do. And you can, if you take about up to 25 minutes if you wish, Clas.
Okay, thank you. So I start by sharing my presentation. I hope everyone can see that. Yeah, and I hope it works if I also make this a full screen presentation.
Nothing has yet. That works.
Okay, thanks. So this is ongoing work with my colleagues Johan Lindén and Christos Papahristodoulou. It's ongoing work, so we don't have so much by way of results, although we have simulations, but there's more interpretation and to do. But so we build a very simple microeconomic model of the electricity market, which is connected to the rest of the economy simply by leaving money for other goods, like in any quasi-linear utility function model. So this is theoretical work with a bit of aid from, well, a lot of aid from numerical analysis. And I think the background for this project is very familiar to probably all participants here. We know that there is a difference between variable renewable electricity. Because it's variable, we know that we cannot so much control the supply of the solar electricity or wind electricity. And that is in contrast with a group of generators that we can call dispatchable generators, the dispatchable supply, like hydro, nuclear or thermal electricity. They are much more controllable and variable, at least some of them. So the well-known problem is that the intermittence of the variable renewable electricity is, first of all, detrimental to the economic value of that source itself, but also it has consequences for other suppliers of electricity, because typically the renewable electricity is has a lower marginal cost and therefore delivers first. So the demand from other sources are getting smaller as we increase the share of renewable electricity. So these are some of the problems that we would try to address here in this paper. What we do is to construct a very small, simple model. It's a theoretical project, but we need to do some numerical analysis. And where do we place this paper in the bigger literature? Well, we think we are somewhere in between two categories of paper. One is a type of papers that we can call consisting of small static models, where much of the focus is on some marginal conditions, some marginal firm, and so on. And on the other hand, we have very large models that are much more realistic, but sometimes a bit less transparent. So we want to maybe be somewhere in between with our model. And of course, if you know any other people who have done something very similar, we are very thankful for references about that. When it comes to the dispatchable supply, you know that there is a supply curve that we often call the merit order, and it reflects differences in marginal costs. The VRE, the variable renewable electricity, it typically has a lower marginal cost and therefore often is delivering first. That is our assumption. And what we do is simply to generate a large number of fictive equilibria with this model. And we use these equilibria to compute different welfare measures, profits and utility and so on. And we do this under different assumptions about the so-called penetration of VRE, the share of renewable electricity in the market. And what we are interested in particular is in, well, the variability of the VRE and also the variability in the demand, and not least the correlation between the two. So that's very much the focus of the model. So I will have to introduce a microeconomic model here with the utility maximization problem. It may seem trivial, but I think it's good not to go through it too fast. So let's start by the setting there. We assume that there's a group of consumers. Let's say that the number of consumers is I, and they use electricity over T hours. The time horizon will typically be 1 year. So T is the number of hours during a year. So we don't discuss so much of investment problems. We more look at profitability and such things given a certain situation in the market. Utility is a function of electricity consumption. X is the consumption of electricity, and the other component of the utility function is Y. That is the money left over for other goods. And the utility function for one person at 1 hour, at one point of time, is demonstrated here. So it's a function of X and Y. The variable theta is a shift variable, which can shift, of course, the demand function. Then follows the utility function. This is a general utility function, which is simply concave, actually strictly concave, in the one argument that we have here, which is X minus gamma. And gamma is something that we call the subsistence level of consumption, a level of electricity consumption that is absolutely necessary for the consumer. That is the interpretation of gamma. And gamma actually is an important component of the model. Then follows a simple linear term where we have money for other goods, and then we have a constant here, which is, of course, the marginal utility of income. And actually, we will make two simplifications from here. So we will put both mu equal to 1 and also theta equal to 1 all the time. But I wanted to keep them in here on the first slide to point to possible extensions. In particular, we think that having mu here opens for the possibility to talk about differences in the marginal utility of income, and that could connect to distributional issues, differences, if there are differences between households. So that's a part of the model. Then we go on and say, well, we sum this utility function over all the hours, all the 8,760 hours of a year. So that's what we do here in equation 1. And we also invoke the budget constraint of this consumer, which is well, the expenditure on electricity, where P is the price of electricity at every different point of time. And then we have the sum of money for other goods. All that should be equal to the total income, M. So given that, we know what to do. We know we formulate the Lagrangian, and in this case, we get a very simple necessary condition for utility maximization, which we see here. It simply says that the marginal utility of electricity should be equal to the price. And that's a consequence of the quasi-linear utility that we have. We can, of course, invert this function so that we get the demand as a function of P instead. So we do that here in principle. So therefore, we have X on the left-hand side. It's a function of P, a declining function of P, of course. And then we have this gamma, the subsistence level of electricity consumption. Of course, we have a downward sloping demand curve, so the higher price leads to less consumption of electricity. But we also note that even if price becomes very high, we will have some demand for electricity in this term over here. So that is a part of demand that always will be there. But it will vary between points of time and possibly also between individuals. Then, of course, we want to come to the market demand. So what is the market demand? Well, it's simply the sum of the demands from the different individuals. So we denote the market demand by capital DT, and it's the sum over all individuals of the demand. And that boils down to this, where to the right here we have gamma T. We have dropped the I because here we sum over all individuals. So gamma T is the sum over all gamma IT. So it's the total amount of subsistence consumption at time T in the market. Again, we have gamma here as an additive term. If we had looked at if you have used the variable theta instead, well, that would have been a multiplicative term instead. But we chose to do it this way. And again, the variation here in gamma will have a central role in our discussion, and it influences the equilibrium, of course, very, very much. Now, let's be more specific and introduce a utility function that we can use for simulation. So we choose the constant relative risk aversion utility function, which of course looks like this. And then we know that the marginal utility will be this term, and we can put that equal to the price and get the demand function in equation 4. So it's an even simpler kind of demand function. Still negatively related to the price, and also it includes the subsistence level of consumption. Going to the market with sum over all consumers, that means that on the market we have the same function here, only that it is multiplied by the number of individuals, I. And here we drop the I because we have summed over all the consumers. So that's the market demand for electricity. Sometimes we will make use of the inverse demand, so we can solve this for P instead and get equation 6. So that would be the inverse demand for electricity. So that's it for the demand side. So let's go on to supply of electricity. We start with the so-called dispatchable supply, DS. As you have seen many times, that supply can be illustrated by staircases, which indicate differences in marginal costs. We will work here in this example with 3 levels of the staircases. One will be called the base load, another is the intermediate, and the third is peak. And you can think of them as hydro, nuclear, and thermic, respectively, if you want. We don't talk about any kind of market power behavior here, so we assume perfect competition. The marginal costs are corresponding to the baseload cost, the intermediate, and the peak cost. So I can jump to the figure describing this. So the supply curve that I talked about is given here. You have the price here, and you have the quantity down here. So the stair for hydro, the base load is down here. For the intermediate, we have it up here, and for the peak, we have it up here. Coming to this point, we are at full capacity. This is a closed model, so we simply don't have access to any more electricity. And then maybe we will follow a vertical curve. At least that is what we assume in the paper. So we have a vertical part of the supply curve like that. What about renewable electricity? Well, the supply is given, is denoted by VT. At time t, the supply is VT. This is a stochastic variable in our model. It's a function of weather, be it sun or wind. So that is simply the supply of renewable electricity. We have a mean value of this variable, which we denote by V bar, and the level of this V bar is also what we interpret as the degree of penetration of renewable electricity. So if we raise V bar, well, we have a larger share of renewable electricity. So again, we have now introduced VT, and we also earlier had gamma T. We are very much interested in the impact on the market equilibrium following from the variability in VT and gamma, and not least the correlation between them, which we'll denote by rho. For this kind of electricity, the marginal cost of supply is typically very low, and for simplicity, we put it equal to 0. Okay, so to come to the figure with supply and demand, it's useful to separate the demand in two terms. So the demand that is not stochastic, the part of demand that is just a function of price, is this term that we saw earlier, but we can denote it by this, d tilde as a function of PT. Then the total demand is, of course, that part plus the stochastic part, gamma T. So that's the demand of total electricity. But then we are also interested in the size of the demand of electricity from the dispatchable supply generators. So what is that? Well, let us define something called the residual demand, RT, as simply the difference between total demand and the supply of variable renewable electricity. So this difference is what actually comes as a demand to the dispatchable generators. And using the demand function up here, we can say that it's also described by this equation. So residual demand is equal to this right-hand side. Of course, then, the equilibrium that we will describe is very much a function of the variation in gamma and the variation in V, and the extent to which they vary together, the correlation between them. So let's come to the figure and combine supply and demand. Supply is already there. What about demand? Well, first of all, we have a curve in the middle here, which is simply d tilde of PT, that the part of demand that is not stochastic, and it's the total electricity demand. It's possible that the residual demand is actually equal to this demand, and that would happen if gamma is equal to V. So if gamma is equal to V, then we have a residual demand here, and that the residual demand is actually what determines the equilibrium. And that would be the equilibrium E naught in this figure. So I'm talking about the case where these two terms cancel out and the residual demand is simply d tilde. But then, of course, there is variation in both V and gamma. So we have a couple of demand curves that capture that. First of all, we have a residual demand curve that we have called R1 here. It's far to the right. And why is that? Well, we have this shift from the basic demand curve to this one because demand is much higher than the variable electricity. The renewable electricity, gamma 1 is much higher than V1, and therefore we have the demand curve R1 and the equilibrium is E1. So that's one possibility. A very high demand pushes the price up one level. Another possibility is that the supply of renewable electricity is higher than the shift in the demand, which we have here, and that gives us the R2 curve, and the equilibrium is down over here in E2. Still the same price as in E0, but the quantity is smaller. Then, of course, it's possible that the supply of renewable electricity is even higher, so that we get a demand curve that is even further to the left. Perhaps it generates an equilibrium like E3 down here. So here we have a case that is much talked about, where the equilibrium, the supply of renewable electricity pushes the demand so far to the left that the price decreases. Sometimes you call this self-cannibalism for V. Of course, it's possible to have an equilibrium on some of the vertical segments of the supply, like we have here in E4. So that would give us the price P4. Okay. When it comes to results, maybe I should focus on what we have. There is something called value factors in the literature, where you construct a ratio between two price indexes. One of the price indexes is simply the average electricity price over the year. So over all the hours of the year, you simply take the sum of the prices, and then you divide by the number of hours. So that's the average electricity price. But then there is some other measure on how much the renewable electricity is paid. So we call this the average revenue of VRE. And to compute that, you first compute all the payments for VRE, the price times the quantity over all the hours of the year, and then you divide by all the quantities that is delivered from VRE, and that gives us the average prices of VRE. And the value factor of VRE then is the ratio between these two. We denote this value factor by V with superindex V, and the implication of this measure is that this number is high if VREs produce much electricity when the price is high, and the other way around. If VRE is producing much when the price is low, well, then this value factor goes down, like in the leftmost point in the figure that we saw. And obviously, it's very beneficial for the VRE if there is a positive correlation between V and gamma, because then whenever demand is high, it happens also that the production of renewable electricity is high, and therefore renewable electricity will have a high price. And the opposite happens if there is low correlation. Then it also often happens that high supply of renewable electricity pushes the price down, and that's generating a low value factor. In the literature, I should mention this before I come to the numerical result. In the literature, there's often the idea that this value factor is decreasing monotonously when we increase the penetration of renewables, and some empirical papers seem to find that. We don't do that in this paper. So this is a bit of a puzzle for us, and perhaps it's could be a point of the paper to point this out. So I skip producer surplus and indirect utility here and jump to the numerical simulation. So for each year, we draw observations for V and gamma from a probability distribution. We use a normal distribution now. We're not happy with it, but it's convenient. So if you have other suggestions, they will be welcome. we have been suggested to use a beta function, so we will see what happens. So we compute an equilibrium for each draw, and we compute the value factor, producer surplus, thanks, profitability, and so on. And then we repeat this in 100 rounds for different levels of rho and V bar. And we compare these computations to see the effects of change in the V bar, the penetration of renewable electricity, and how it is depending on the correlation. So when it comes, I'm not so sure you can see this, but I can tell you what it tells us. These are two figures on the value factors. So let's focus on that. The value factors are measured on the vertical axis. On the horizontal axis, we have V bar, the degree of penetration. This is rather high, unfortunately, but it doesn't matter. We have three curves depending on the correlation between B and gamma. So the upper curve is the positive correlation, so that keeps the value factor high for this type of electricity. With negative correlation, it's much lower. But we see two things here. First of all, the levels of the value factor is about seldom below 98%. In the literature, it could be 70% or even 50%. So we are not able to get the value factor as low as in the literature, even if we experiment with high stairs. And also we have this wave pattern. The value factor goes down, but then it goes up. And the interpretation is that it can go down because when we have more and more renewable, well, it tends to push the price down for renewables. But if there is even more renewables, well, then that also tends to push the price down on average. So therefore, all types of electricity gets the same low electricity price, and that explains the upward sloping part of this curve. So maybe I have run out of time now, or what do you say?
Yes, because I'm afraid, well, I'm happy to say that Fabien has, I think there was a breakdown in communication, but Fabien is now in the session. And so I've sent you a couple of messages to sort of do things a little bit behind the scenes. Welcome, Fabien. If you could let me know in the chat whether you would prefer to sort of take the slot that's not so far from when people are expecting you, and puts Nicolas in the slot that people were expecting, or whether you'd still prefer a few minutes to get your head together. If you could do that in the chat, while otherwise, I thank Clas, and do people have any questions on this presentation, please? I've got one, which is, are you changing your supply curve, Clas, as the amount of renewable energy changes?
So far, we don't do that, but we have talked about doing that. And in particular, we have also talked about changing the hydro in the short run by regulating the hydro. But of course, in the longer run, we have it in mind, but in this presentation, we don't change it. So it's a constant supply curve on the dispatchable part.
Okay, because I've noticed sort of empirically, Germany had a big decline in prices as renewable output increased. And I suspect, although I don't really know the market that well, there may be people here who do, that that was partly because their conventional capacity maybe didn't change so quickly, whereas at least up to a few years back, the British price didn't move so far away from the sort of inferred average marginal cost, annual average price versus annual average cost of gas and carbon didn't change very much, but we were closing older power stations about equivalently to the increase in renewable capacity. And so that may be the sort of thing that would might change the behavior. And then it's a question of empirical question of which one is a better representation of what actually happens.
Mm. Yeah, thank you. We will certainly keep that in mind when we look at the profitability of in particular, the peak section, I think.
Yes. Okay. Do we have any other questions? I'm keeping an eye open for any hands that are coming up. I'm sort of slightly conscious that I'm not seeing them. I think it's interesting to have the focus on consumers, which so often people just say, here's a demand function, and go in from that rather than sitting back. So it'd be interesting to know, how much the consumer welfare is changing, and also perhaps what the renewable revenues are relative to everything else. But anyway, sorry, I'm sort of having to do about 3 things in my head, because Fabien, would you prefer to go now, or would you prefer to go in a few minutes' time? I suppose I should also be giving Nicolas a thing.
Good morning. I'm happy either way, as you prefer, Richard.
Okay, and are you? And the other question is, are you set up for sort of a full-scale presentation, or the chat I had from our session host was you agreed to do a little presentation?
Yes, I can do a 10-minute presentation of that.
Yeah, if you feel that is acceptable, then if you were willing to do that now rather than the full slot, because I was giving time to our first 2 speakers, then we could finish on at the expected time with the previously expected time for Nicolas, and everyone still gets 15 minutes before the plenary session. So in that case, thank you very much. And as I say, communications didn't work, but very glad that you're with us now. So Fabien Roques, also talking about European market integration.
I hope you can see my screen, and apologies for the mess up. It's entirely my fault on the confusion of time zones, essentially, for this session. But I'll try to be brief and speak about the integration of European electricity markets. It's a paper that I have written, and that's going to be published as part of a book edited by the Foreign School of Regulation, and to be published this summer. It's essentially a qualitative paper that tries to look back at what we have achieved in Europe with integrating electricity markets, and tries to also look ahead regarding the challenges we have. And essentially, I will cut a long story short and say that we have achieved a great deal. We should, recognize that it is really imperfect, of course, what we have now. But the issue is not necessarily in the market design itself. It's in the integration of the underlying policies. So that's going to be my first point. Policy and governance coordination are prerequisites to further integration of market design. And then I'll spend probably a few remaining minutes highlighting what I believe are the top 2 or 3 issues for wholesale market design. So we all know the clean energy package. It's kept a lot of people busy in the past 5 years in Europe. And it's actually, the culmination of 20 years of debates on market design and integration. What has it got in it? Well, it's got very useful legislation in terms of, I would say, the role of regulators, the role of TSOs. It's got very useful stuff also on coordinating in the short-term power markets. I'll come to it in a minute. It's got some, I would say, start of coordination for renewables and energy efficiency. But this is where really it's proving challenging. It's coordinating the underlying policy. So if I look back and analyze this package, what can we say? Well, we have a focus on decarbonization and integration, the top 2 that you see, but this is actually raising a lot of questions. We don't have a holistic cross-sectoral approach. I'll give you a few examples. We haven't answered the big question as to what is the right level of subsidiarity, meaning what should be decided at a national level, what should be decided at a European level. And we haven't got right yet a wholesale market design and system operation that is focused on the short-term issues. What I mean by that is with the growth of renewables, we need to move the system closer to real time. That's my introduction, and I'll say a few more words on why the change in context requires a change in market design. And then, as I said, I'll focus on the key issues I see going forward. So the context in which we are now is markedly different from the context of the 90s and 2000s for market design. The focus then was on integration, almost exclusively. It was almost a competition policy, to be honest, driving energy policy. The focus today is on decarbonization and security of supply and affordability, but that's not just integration. The market design was essentially built in Europe around the day-ahead market integration. We implemented market coupling on the day-ahead. We are now turning to the intraday and real-time markets. Technologies are different, growth of decentralized generation. Consumers are different. They are a lot more engaged. Demand response is coming in. And on the network side, we all know the issues as well. So what does that all mean? Well, that means essentially policy and governance are the key to further integration. And I'll give you the results of a literature review I've done. So this is a literature review trying to summarize the estimates of the gains of more coordination in Europe by theme. So you see that the integration of the wholesale market has been widely quoted as bringing benefits to the order of €1 billion per year on the left-hand side. It's a figure that the European Commission has been very proud of. And it's confirmed actually by a number of studies. Obviously, there are variations in how you estimate that, but that's a ballpark estimate. If you take that integration further intraday and for balancing, it's probably the same order of magnitude, if not more. I have seen studies ranging from 0.3 to €3 billion gains per year. If you focus on demand response, the studies I have surveyed give you between 0.5 and 5 billion gains per year if you have an active demand response. If you coordinate investment across Europe by sharing reserves, for instance, for adequacy, it's between 1.5 and 5 billion gains. If you coordinate network and generation planning, studies I have seen are between 3 and 6 billion per year gain. And if you optimize renewables deployment and suppose that you can also deploy the network so that there isn't too much connections, you have gains which are between 5 to 10 per year. What does that tell us? Well, it tells us that what we are focused on, which is creating integrated markets for the day ahead, is valuable for consumers, but that there is potentially a lot more to gain in Europe by focusing on the harder integration of underlying policies for renewables, reserves, networks. And I think that is a key issue going forward. I have in the paper a number of examples of these coordination mechanisms between networks, generation, local resources, but I don't have time now since I promised to you reach out to speak for 10 minutes. So I'll skip a few slides on these examples and then focus on the second point of the paper. What are the key areas of focus post-clean energy package for electricity markets in Europe? I have essentially 3. You'll tell me there are many more, but you need to choose. I think the first one is really reflecting real-time system conditions given the growth of renewables. And there is a lot of work that is being done on what is called scarcity pricing and better integration of reserves. The second theme is congestion and the good old issue of nodal pricing, or actually locational price signals. And the third issue is the reality check, as I call it, if we assume that policymakers want to control the mix. So there isn't going to be free entry and free exit in the market, which is one of the fundamental conditions of dynamic efficiency in the market. What is a good market design? So these, to me, are the three main issues. On the first one, on scarcity pricing mechanisms, this is an issue that has been well explored in the literature and actually in practice. If you look at the US, in Texas, in other states, there's quite a lot of experience with ORDCs, operational reserve demand curves. The key question in Europe is how do you make that compatible with our design, which is quite different. There are a number of useful papers looking at this, which I survey in my paper. I won't say more. If we look at network congestion and coordination, you just have examples here of the cost of congestion going up, both in the UK and Germany, two of the countries that are experiencing the greatest issues regarding congestion. Well, what we are seeing is actually the comeback of that whole debate on zonal versus nodal pricing. In Europe, we have chosen the zonal approach. The US, New Zealand, Australia have gone for nodal pricing. All things that we need to revisit that debate, not necessarily to implement nodal pricing, but to implement some form of locational price signals. And I think we are actually doing that in Europe as we speak. Local flexibility markets are emerging in a range of places and countries. And I have worked with one of my PhD students, Theodore, to actually survey these different flexibility platforms. And I think that's actually a way towards locational prices. I'm going to finish with the last issue, which is, again, if we have to design a market design around the fundamental assumption that there is not going to be free exit and free entry in the market, that the mix is going to be driven by policymakers, which, by the way, is not new. If you look at history and at that chart, there's been actually quite little, by and large, merchant investment driven by free entry and exits in European power markets. That's the reality. So if we acknowledge that as a starting point, what is a good market design? And I'd say, well, we need to distinguish the short-term efficiency dispatch, which can be driven by short-term marginal cost, from the long-term profitability. And we need competition in two steps, which is well known, by the way, in other industries, which share the same characteristics as the power sector, meaning being capital intensive, and where policymakers essentially are driving the evolution of that capital stock. So competition for the market is typically organized around tendering, auctioning of some form of long-term contract, which can be technology specific or technology neutral, will put the competitive pressures where it matters. CapEx can be used to stimulate new entry, so can be used to be pro-competitive rather than anti-competitive, and can also be a new way to ensure a coordinated system development. This can be followed by competition in the market, which is what we have. Integrated power markets, where essentially we can continue to integrate better the dispatch, the intraday, and the balancing. So essentially, that concludes my presentation. Richard, I promise to stick within 10 minutes, but the big messages are, we need to account for the fact that you don't design a market in a vacuum. You have to take into account what are the underlying policy objectives. You have to take into account what are the underlying technology characteristics and the characteristics of consumers' demand. And these are all changing. With decarbonization, policy intervention is here to stay. It's quite different from the assumptions we had only 20 years ago. And what are then the big issues? Well, I think I have listed two. One is we cannot integrate our power markets in Europe further if we don't integrate further our underlying policies on some of the key issues. And the second one is, well, we need obviously to work on some of the details of the market design in the short term regarding networks, but we also need to plan for this competition in two steps, which will mirror the reality of policymakers' involvement. So I'll stop here. Richard, thank you very much.
Thank you very much, Fabien. Are there any questions? Again, if you raise hands or just possibly put something into the chat. How far do you think we could have, fairly standard contracts, or how far do you think they might need to be tailored to the types of plant that are going to be bidding for them, in which case would policymakers be segmenting the market?
I think we need to be very careful of standardizing contracts, because policymakers and regulators have typically a pretty bad track record of identifying the menu of contracts that's optimal. I think what should be fostered is some harmonization of some of the basic principles to avoid distortions in energy markets. So for instance, what we have done with capacity mechanisms is making sure that you don't have long-term capacity contracts which are interfering with energy activations. So you harmonize the underlying principles, but then you leave it to the market to actually generate that menu of contract and to self-select. That's my personal view. I know that others in the literature have put forward the idea of a market, for instance, for long-term contracts, which assumes a fairly high degree of standardization, if you want to be able to, have a secondary market. I think it's going to be very challenging to design a one-size-fits-all, type of contracts that would work, in my experience. We could perhaps have a slightly limited menu of contracts, but I'm skeptical that we can have, a one unique design. Richard.
Okay, thanks so much. And there's a quick question. Flex has come in on the chat from Astier Nicolas. Sorry, I missed. Apologies for my appalling pronunciation there. For flexibility markets, do you think there are aspects that should be harmonized by regulation across Europe, or is it better to leave them to develop first on their own? Very quick answer, or a quick answer, and then anything else you want perhaps in the chat.
I think that's an excellent question. I think there is a time for experimentation where essentially you get benefits from innovation, trial and error. And we are probably in that period for flexibility markets, to answer in a quick way your question. Now, at some stage will come a time to define the principles. And again, what defines principles is essentially in Europe ensuring that you don't damage what we have created, which is an integrated energy, a set of energy markets. So I think at some stage there will need to be at least some guidelines as to what is a minimum, I would say, common denominator and what should not be done according to best practice. But again, I am against some, I would say, early standardization of a given design, because I don't think we have yet experimented enough to understand what's best.
Okay, thanks very much indeed. And as I say, thanks for your flexibility on the timing. But Nicolas, we will be a couple of minutes into the break, but that's what breaks are for, I believe. So over to Nicolas working with Martin Overle on reliability standards.
Thank you, Richard. I should be able to keep it until the break. It's pretty versatile presentation, hopefully. So thanks a lot, Richard. So I'm Nicolas Astier. I'm currently a postdoc at Stanford, and I'll be joining the Paris School of Economics in September. And this is joint work with Martin, with Ghent University, and also affiliated to Yale. And it's a fairly simple story, actually, but it took us a while to put all the pieces together. So we're really looking forward to your feedback, comment, and suggestions for our next step, because also hopefully the thing is that I'm going to tell is going to sound pretty intuitive. It took us some time to sort things out. So we are a crowd of people passionate about electricity markets here, but for the average citizen, maybe for a grandmother, well, they only care about the electricity market where something goes wrong. And to give an example, this is a classic Google Trend graph that goes all the way back to 2010. Look at the search intensity of the keyword ERCOT, which is the system operator in Texas. And so what you see that pretty much for 10 years, nobody cared about it at all until we had this outage in February, and now there's this big spike. So basically that kind of illustrates that average citizen or the median voter, if you wish, kind of care about the electricity market mostly in terms of prices. And because this is the case, and policymakers and politicians are very aware of it, even in places where wholesale markets are liberalized and competitive, there are a bunch of heavy-handed policies that tries to avoid blackouts from occurring. And so in jargon term, that is try to ensure generation adequacy. And so what you can see, for example, in this map from the ACER's market monitoring report of 2019, that all the countries in yellow or red have some kind of capacity remuneration mechanisms that say that basically they provide additional remuneration capacities for being online, regardless of what they're producing. And what's even more interesting is that all these countries in red have this in place, even though their own assessment of whether they face a capacity shortage in the medium realm says that there is a very, very, very low probability that anything wrong will happen. And so these countries feel the need to have some kind of mechanism to ensure generation adequacy. And the way a country tries to enforce generation adequacy is to set what we also call in jargon reliability standards. So basically what you want to see with what you want to do with generation adequacy is to determine how much capacity you need in the medium and long run to have to avoid blackouts. Or say differently, you want to check if some kind of long-term scenario won't lead you to a situation where you might have blackout. And the way this reliability standard works is like you try to assess, you look forward and you try to assess what's the expectation that an outage will occur. So the last piece of jargon, I hope, so the word for that is the loss of load expectation. So what's the probability that you will have to curtail load at some point in the future, which is often expressed in hours per year. So you kind of try to assess this number, and what the reliability standards does is it gives a target threshold that you shouldn't exceed. So for example, in the US, it would be 2.4 hours. In most of Europe, it's 3, but you can find countries where it's 4.8. I believe 8 is for Ireland, where the talk from there in the beginning. That's how these things work. And this is, for example, in France, it's in the national legislation that this has to be somehow enforced. There is a good microeconomic foundation for these reliability standards. I think most of you are aware of it, but I'm just doing some very quick energy economics 101 here to make sure everyone is on the same page. So the way you try to assess generation adequacy in your microeconomic textbook is while you look in the future and you try to think about what's the distribution of hourly load I will face in my power system. And so what you do, you rank them in decreasing order to build what engineers call the load duration curve. So this is this curve that tells you for a given level of probability, so the number of hours per year in expectation, how much load you will get. So basically, if you're worried about, let's say this is, I don't know, 100 megawatt, and you kind of want to guess how much, you kind of want to assess what the probability of exceeding this level of load. While you take this level, you go to the load duration curve and you go down to the x-axis, and you get your probability of exceeding this demand at some point in the future. And so from this load duration curve, you could use what people sometimes call screening curves to determine how much capacity you should install. Sorry for that. So basically, if you focus on the hours with highest amount of load, well, your trade-off here is, should I build more peaker technology to avoid curtailing load, or should I just curtail load? So if you curtail load, you don't have any capacity cost to incur, but you have to incur what is called the value of lost load, which is the opportunity cost of non-consuming electricity for consumers. And if you want to avoid that, you can add 1 more megawatt of peaker technology. This has a fixed cost, which is in administrative term these days is called the cost of new entry fixed. And you have a variable cost, which is the cost of new entry variable. So that gives you this, this cost curve for serving a given duration. And basically where these two curves intersect gives you the optimal level of reliability, where basically the trade-off between curtailing load or installing more peakers is met. And you get this very simple reliability standard, which is this ratio of the capital cost of new generation over the value of lost load minus the variable cost of new generation, which is negligible compared to the whole. So this is microeconomic funding that works well. And we've known that for a while. So Richard being our chair today, I think it would be appropriate to cite a British economist here, especially given there is some history between French and British economists. So we can fairly say that it at least dates back to Turvey in the 60s. Maybe some would think that Boito said it before, I don't know, but that's the further we could go back in time. And so this is known for a very long time. The issue with this model, so that there are plenty of assumptions, especially relating to what Fabien just said. So there are many things that are changing in electricity markets that kind of question the micro foundation of this, like the assumption behind this reliability standard. But the one we're interested in this paper is what I just told you works for a single country. Like I taught you a single low duration curve. That's a single power system. Let's say Great Britain, let's say France. And what's unclear is, does the enforcement of a national reliability standard still works when you start being interconnected? So when these things were developed, it was again in the 60s, interconnection capacity was basically zero. Now that we have much more interconnected system, we're still using these standards because there is a lot of inertia in keeping them due to all this political environment. So we're still using them, and they're still microfunding on this historical reason. So does it still make sense when you start to interconnect? And the two-step question we are kind of interested in is, should we update them, replace them, and how should we think about coordination in an interconnected system when you have these kind of things? And so if I have to rush to the end, quick summary of results, we have a theoretical part where we kind of show that at least to our surprise, you can still use national reliability standard in a way that makes sense from a microeconomic perspective, but you need two conditions. First, you need to have some kind of coordination. So you have to make a right assumption about how much capacity your neighbors is going to install, and that requires information, coordination, and these kind of things. And second, you need to account in your loss of load expectation calculation the externality of your capacity, the positive externality that your own capacity has on your neighbors. Because there might be hours where you meet your load, but if you had 1 megawatt at home, you can actually help the neighbor more, and you have to take that into account in your load calculation, which you might not do if you don't pay attention. And we run the numerical simulation for Europe and kind of find the first aspect of regional coordination matters the most. All right. So in terms of how generation adequacy assessments works in practice, so as I told you, the current approach is basically inherited from the history. So the current approach is basically each country makes its own generation adequacy assessments. And doing so, it has to make assumption of about its neighbors, how much capacities they have, how much import is going to be available, how far do you go in modeling the full power system in a place like Europe where you have like 20 plus countries. Should you model them all, or should you just use the first ring, the second, all these kind of question you have. Whereas from a purely engineering point of view, leaving aside policy debates, well, the simple optimal approach would be to just optimize everything altogether. However, because of this political nature of ensuring generation adequacy, it seems likely the national decision maker, national politician will be quite reluctant to transfer the responsibility of generation adequacy to supranational level. So and to illustrate that, it's kind of interesting to look at Europe, because as Fabien mentioned, we just enacted this clean energy package. Within this clean energy package, there is a regulation about risk assessment. This regulation mandates ACER and NSOA to put in place a regional adequacy assessment. So basically, they have to come up with a way to make sure that generation adequacy is met at the European level. But this methodology will use as input, national input about reliability standards and the value of loss load. So even though there is this directive, you still have this hybrid approach of national reliability standards and a regional assessment. And so basically what we were wondering is how can you make sense of that? So the framework, the theoretical framework is really simple because as I hopefully explained the motivation, we really try to change one thing at a time. So we start from this benchmark where, which is the traditional model where where reliability standards come from. And we just change one thing, which is now countries are interconnected. Because of that, we make very, we make assumptions that are used to be standard, might not stay standard in the future, but bear with us. So in terms of demand, we call DI the hourly demand in a given country I, V is the value of loss load, and this is supposed to be inelastic and non in a stationary way. So we denote KI as the total capacity. We assume that each country has the same peaking technology, so that this fixed and variable costs are the same for all countries. And what we add compared to the way reliability standards used to be assessed is now we have, well, in what I'm going to show you 2 countries in the paper, we also extend to N. So countries are interconnected with some interconnector capacity. So for 2 countries, it doesn't matter that much, but for N countries, we use a net transfer capacity model. So we don't model power flow, and because that's how it's going to be implemented, at least in the short term, by Acer. So we just introduced one notation. So we call alpha the autarky reliability standard, so that the formula I showed you on the graph before, so that just basically the 3 hours per year you would have in France or 8 you would have in Ireland. So that's the historical standard that is derived from a country in isolation. And so historically, or what's still in the law, for example, in France, is that loss of load should target this reliability standard. Now when you have 2 countries, you cannot just do a one-dimensional graph where you look at when you curtail, you have to consider the joint realization of demand of both countries. So in this graph, you have demand in country 1, demand in country 2, how much capacity country 1 has, how much capacity country 2 has. And basically the demand can be served in all this demand realization in the right area. And if the pair of demand in country 1 and demand in country 2 fall in the gray area, then you have to curtail some load. Because if you're here in country 1, the demand is higher than total capacity with import capacity, same thing here for country 2. And if you're in this region, the sum of demand is higher than the sum of total capacity, so you have to curtail load. And what changed compared to the single country case is that now you might have some ambiguity of which country you're going to curtail first. So if you take the perspective of country 1 and you ask, okay, in which demand realization you're going to be curtailed, when in practice what's likely to be happening is you're going to be curtailed in this gray area. So basically, whenever demand exceeds your capacity, or whenever you cannot import more, and your import will be limited by the fact that the other country is itself experiencing low load. So basically, its demand is higher than its own capacity, so it will curtail export. But you could imagine a situation where all low load in this region is shifted to country 2, where even though they could, and basically what the second country could use a capacity to export, even though it has some scarcity, domestic scarcity itself. So there's some ambiguity about how you assess the loss of load in a given country. And so when you write this optimization problem and try to say, okay, what the first order condition is, graphically, that's how it gets. So if you write the first order condition with respect to the installed capacity in country 1, you get that the weight of this region should be alpha, which gives us 3 takeaways. Well, first, to compute this first order condition, you need to know what the optimal capacity in your neighbor. So you kind of need to coordinate to figure out what this capacity is. Second, you have to compute this loss of load expectation while taking into account these hours where you could keep your capacity for yourself, but you could also help your neighbor And since you could have hours where if you prioritize your own domestic load, you don't have load in your country, but your neighbors have some difficulties. And if you add 1 more megawatt in your country, you could help your neighbor more. Then you have to account for these hours in how you compute your loss of load expectation in your adequacy assessment. And the third takeaway, which is actually surprising to us, is that this weight here is actually this alpha, which is the same autarky reliability standard you used to have in your country. So you basically, you can still use your autarky reliability standard as long as you coordinate on your assumption for your neighbor capacity and you internalize externality effect in terms of security of supply. So I'm going to rush to the simulation because there's only 5 minutes left. But basically, then what we do is we take public data from an NSOA transparency platform and kind of implement these steps, these scenarios in steps. So we look at an autarky scenario where each country installs its capacity, ignoring completely its neighbors. We look at a national adequacy assessment where each country accounts for its direct neighbors, but makes the assumption that they will install their autarky capacity. So they kind of misrepresent how much capacity they're going to have. Then we have a regional assessment where they coordinate on the capacity, but compute the loss of load expectation wrong in their adequacy assessment, so they don't internalize benefits. And then we have the optimal benchmark. So I skip through the data. So we do that for a set of 11 countries in Europe. And what we find is that basically when you coordinate at the regional level, you basically grasp most of the benefit that leads you towards the optimal. So the absolute value of cost here doesn't mean much because we assume that the peaking capacity is the only technology you have, but basically what you see is that going from regional to optimal saves you like 10 million euros per year, which is very small. By contrast, if you make wrong assumption about how much capacity your neighbors are going to install, you could get much more costly scenario, because what's happened here is kind of over-rely on input in your simulations, which turn out not to realize, and then you have to curtail a lot more in the short term. All right, so this is the same summary slide as before. So what we are interested in is try to understand whether keeping or using a national reliability standard can still make sense in an interconnected system. And to our surprise, what we find in the theoretical framework is that it actually can be the case under 2 conditions. First, you need some regional coordination, and second, you need to internalize the external adequacy benefits of your own capacity on the neighbors. And in our numerical simulation for Europe, it seems that regional coordination matters the most, which is good news because that's what ACERS is currently working on. So, well, welcome any feedback. Hopefully I made it on time. Yeah, there's 3 minutes left for questions. Thanks.
Okay. Thank you very much, Nicolas. And as I said, it's socially acceptable to leave at the moment of the break, but I think hopefully there's time to go into it a little bit for if we've got a lot of questions coming up. As before, please do use the reactions button at the bottom and the sort of raise hand if you've got questions, or you could put something into the chat. But my thought was, it's interesting stuff. Did you identify any country? I see that when you went from autarky to national, capacity went down, and then to regional it went up. Did you find any countries where when you went from national to regional, the capacity actually went down? And would you be able to sort of dig a little bit to try and get intuitive explanations of why that might happen? Just thinking that might be an interesting sort of inside the black box thing to do.
Yeah, that's a great question. So we do also have in the paper like simulation where we do only country pairs to kind of understand what's happening a little bit more. So from regional to optimal, the capacity goes up because basically if you do a regional assessment without computing the loss of load expectation correctly, then you miss all hours where your capacity, the value and your spare capacity could be, oh, sorry, I want to say it right. So there are hours where if you say you use your capacity first for yourself, then you won't have any loss load in practice, but you might have a neighbor who's himself is having loss load, and if you had more capacity, you could help him more. And so there is some social value of increasing your domestic capacity. So that's why in the optimal case, you get more capacity, slightly more capacity than in the regional case, because you internalize this external benefits. Now from national to regional, we get the other way around, because we kind of, this comparison can go either way. Here we kind of made the assumption that when you run your national adequacy assessment, you assume that your neighbor country will have autarky capacities, which is a very naive and myopic assumption. And because that turns out not to be the case, you kind of overestimate how much you can rely on import. It can be very well the case that you make the opposite assumption, that you kind of make very conservative assumption on how much import is going to be available, and then you kind of downgrade imports a lot and overinvest. So this comparison between national and regional, you have to model countries' mistakes, and it's very hard to model mistakes in the right way, I would say. So it's, yeah.
Okay, thanks. I see Lisa has a question.
Hi, thank you, Richard. I thought that was a really interesting presentation and idea overall. I suppose my question is a little bit more practical in terms of, like, do you see evidence of this happening at regional level in Europe? And is there a mechanism, like, is that at Acer that they can do so? And also, what are the cost implications, like from a system perspective? It would like reduce costs overall, but in the short term, or like, how are those costs distributed as well? So it's kind of a practical side of this question.
Yeah, those are great questions. So in terms of practical side, yes, because basically the directive mandate Acer and ENSO to come up. So they published some initial draft for the guidelines at the end of 2020. So there is one about adequacy assessment, one about reliability standards. So I mean, this is very much in the administrative process in Europe, and currencies are very they don't go in much detail on how they compute loss load expectation. So that's also something that yeah, we find interesting, is that it's hard to tell if they do it the right or the wrong way, because right now the documents are at an early stage, so it's unclear whether they're going to do it like this or not. But we hope to contribute to that. In terms of distributional, we don't dig too far into that, for the very simple reason that these NTC models. So I mean, it's a very flat optimum with very contrasted outcome at the country level, like because it's you don't take like physical construct of networks. Like nodes are very substitutable one for each other. So there are many occurrences where installing 1 megawatt in one country versus the other doesn't change the outcome much. And so digging into what happened in a single country is very unstable. Although the total cost is very stable, what's happened in a single country when you don't have a physical network model, yeah, it's kind of a an act of fate, I guess. So yeah, we don't go too much into that because we're not convinced that NTC models are the most appropriate to do that.
You would think there would need to be some kind of incentive mechanism to encourage a country to, I suppose, invest in that positive externality, as you say, it is an externality.
Yeah, I mean, you said capacity mechanics. It's just a matter. What's nice about it, it's just a matter of how you run your generation adequacy assessment. In real time, if you prioritize your own load, it doesn't really matter, because you are at the right amount of capacity, and whether loss load occur in one country or the other, if the voltage is the same, doesn't really matter. So it's just a technical details about when you run your simulation as an engineer. So you shouldn't model the loss of load expectation as you think it will occur. You should model the loss of load expectation as an economist will do it. So yeah, it's just one of the situations where economists and engineers have to talk to each other.
Thank you. Sorry for interrupting.
Okay, thanks so much. Yes, I'm conscious that in the northeastern United States, they've had capacity markets for a long time, and I think they've probably had rules and debates over whether stations in one area can be involved in another area and how. And there was a bit of debate on the British market when we had a capacity market, initially ignoring the fact we were an interconnected country, and then possibly because David Newbury pointed out that had disadvantages, we started taking account of it. So David, I know, has written on that. So those might be a couple of things to look at if you haven't already. So.
Yeah, thank you.
Otherwise, I am afraid I have stolen 4 minutes of your break, but I hope you will agree that it's worth it. We can probably create a complete online cacophony if people unmute themselves and just either that or put your cameras on, but sort of virtually thank all of our speakers. And also a big thank you to the session host, whose name I don't know to be slightly more personal, but we couldn't have done it without you. So thank you very much, everybody.
Thank you, Richard.
So enjoy the break and the rest of the conference.